Last time we took a look at section 8.5, equations in a Cartesian coordinate system, and we looked specifically at the Cartesian coordinate graph, model, the coordinate systems, and then we did it with respect to points and lines. That's what we did last time. And what we're going to go into today is systems of equations, which means actually where two lines cross, or maybe they're parallel, that kind of stuff, okay? So we're going to look at systems of equations today. A system of linear equation is a set of equations, usually with more than one variable in each equation. A solution to a system of linear equations is an ordered pair belonging to each of the lines, because linear equations are lines. That is, it's an ordered pair xy that is common to or satisfies both equations. And graphically, that looks like it's an intersection. It's where they cross. So as we look at finding solutions to systems, we're looking at some kind of an x and y value, and they're referencing it sometimes with a and b in your book, but an ordered pair value that works in both equations, and graphically that means it's where the equations cross one another. Okay? There's multiple ways that you can actually find such a thing. One of them is simply by graphing. And if the graphs are simple and you've got a good sense of your, you've got like a graph paper or a dot grid or something where you can be very precise, graphing's not a bad way. And in fact, it's one of the earliest ways kids learn to actually find solutions to this, because they learn how to graph and they can see where they cross. It's got great visual appeal to it, so for those who are visual learners, it's really wonderful. But it doesn't work if things end up being not integer values. It becomes very complicated. So if something crosses in between two values, is it really 1.5? Is it 1 1/3? Is it 1.37? You just can't see it very well, right? So there's a couple other ways that we can actually look at where graphs cross that are a bit more precise, although they lose some of that hands-on visibility that you see with a graph. One way is called the substitution method. So we're going to go through the steps of the substitution method first. So you solve one equation for one variable, and it doesn't matter which equation, it doesn't matter which variable, you get to pick. You substitute this value into the other equation, and then you resolve that equation. In doing so, you'll find out x equals something or y equals something. You back substitute that value for your answer into the other equation, the first equation you started with. And then the last two steps, or the next step, step 5, is really not something you write down. It's more of a, you're going to check it because you would want to know that you're right. You're going to check your solution, at least mentally, by plugging both values into the equations. And then on step 6, you're going to write the solution either as an ordered pair, right? Parenthesis, x value, comma, y value in parenthesis, okay? Or if it's a context-related question where you're finding numbers of shirts and numbers of pair of pants that somebody, bought at a flea market or whatever, I don't know, whatever they did. You would actually write this number with the units of what it is and this number with the units of what it is. So if it's context, it's going to have units. If it doesn't have context, it's going to be written as an ordered pair. And we're going to do one that's like that, got the context. So, at a movie theater, a child's ticket costs $5 and an adult ticket costs $8. On Memorial Day, the theater counted 562 audience members, and they had a total of $3,785 in ticket sales. How many child tickets and how many adult tickets were sold? All right, so in some sense, if you look at the steps here, we can't even start at step 1. Why not? We don't even have any equations. So we're going to have to start sort of, this is like step 0. All right, step 0 is figure out what the equations are when you're given a word problem. So with the word problem, we're going to have to figure out what the steps are. So what are the two things that I'm asked to find in this problem? Yeah, and I like the way that you guys said this because you used the phrase how many, right? It's the number of. So the first thing we need to do is we need to write down variables for those things we don't know. And we might as well let them be x and y. If you want to let them be other letters, more power to you. But I'm going to call x, that's going to be the number of child tickets sold, If you just write child tickets sold, that's not the same thing. That's not what X is. X is the number of them. Okay? And then we can let Y be the number of adult tickets sold.
Do we always need to write that?
You do. You need to clarify what it is you're letting your variables be, both for your benefit and for mine. So in terms of for my benefit, it allows me to see if you've got an error in your thinking, what's actually causing the error. Are you defining your variables incorrectly, or are you setting up the equations incorrectly? Does that make sense? And the same is true somewhat for your benefit, but also for your benefit at the end, you need to know what X was to know what you found, so you don't end up reversing the values or something like that accidentally. Yeah. Okay, so we've defined what it is our X and our Y are going to be. As we're looking at this next, we're going to have to create two equations. What are these? I don't want you to give me the equations, but what are they going to represent? There are two quantities being measured here. What are they? The number of tickets and how much money is being made. So these are the two separate equations we're going to have. One talking about how many tickets and the other one talking about how much money. Let's do the number of tickets first because it's the easiest equation. What would the equation look like for the number of tickets? Right, X plus Y equals 562. X is the number of child tickets, Y is the number of adult tickets. If you add them together, you should get the total number of tickets, and that's the 562. Okay, now we're going to do the cost one. So let's think about the child tickets. There are X child tickets sold. How much do the child tickets cost? $5. So if you were asked to find how much money was made by selling child tickets, what would that expression look like? 5x. Okay? Because it's multiplication of how many tickets times the cost of the ticket. The cost of the ticket's 5, how many is the x. And then what would you do for the adult tickets? 8y. What was it, Leah? 3,000? 780? 85. Sorry, my screen is maximized so I could write a little bit bigger for you. Okay. So this would be our value of money that's being acquired by this movie theater. Okay, so we actually are at the point now where we can do step one. All the work is not even step one. Okay, so I'll number my steps. You don't necessarily have to number your steps along the way, but this way you have them numbered if you want to go back and be like, what was it I did next, and relate that back to our list of steps. What did the first step say is where we start with substitution? Solving one equation for one variable. And well, in theory, we could solve any four of those quantities, the x or the y in the first equation, the x or the y in the second equation. There are things that are easier to solve for than others. Agreed? Okay, somebody tell me something that would not be easy to solve for. Y on the bottom one. Or even x on the bottom one, right? They've got a multiplication factor in front of them. I wouldn't want to do that. But either the x or the y in the first equation are pretty straightforward. So which one would you like to solve for, x or y? X. Okay, so x is going to equal what? 562 minus y. So that's step one. Now step two is to take that quantity and to substitute it into the other equation. So the other equation started out with 5x. So instead of having 5x, we're now going to have 5 times 562 minus y plus the 8y that was already there equals this 3785. That's step two. Okay, this is the location where x was before, and now it gets replaced by what x is equal to. Did everybody see that one okay?
And then you said, like, when we're solving this, we can do arrows, like, say we distribute the 5.
Yes.
Can we do, like, an arrow?
You can. So, yeah, so if you like to, some of you like to write across the page instead of down the page. That's what Hannah's asking about. So if you're writing across the page after this step and you want to draw an arrow to say, and my next set of, my next equation is, that's fine. I write down a page so I don't have to worry about notation between them for that very reason, Hannah. But if you really want to go across, yes, you would use an arrow or something to indicate that. All right, we are going to distribute this next. So if we distribute through the 5 here, what's 5 times 562? 2,810. Don't forget the 5 also has to be multiplied by the negative y, so that's negative 5y now. All right, what would you like to do next? We have 2 options.
Combine the y's.
Combine the y's. Okay, so the 2810 can stay put. And if I combine the y's, what do I get, Emily? 3y. Very good. And then it equals 3785. Oh, did I have my sign wrong? I do. Thank you. Yep, you're right. It's positive. Okay, cool. What's our next step? Yeah, we need to subtract the 2810. 2810. Okay, so what is going to be left on the left? Just the 3y. By the way, I'm doing step 3. Let me write that there. What's going to be remaining on the right? 975. What's my next step? Solve for y by dividing by 3. And what is 975 divided by 3? 325. Okay, so just pausing for a moment. What did we find? The value of y, but what is it? We found the number of adult tickets sold. Okay, so we found the number of adult tickets sold. We'll use that in a minute. Before we do, we actually were asked to find the number of not just the adult tickets that were sold, but the children's tickets, right? Hang on, sorry about that. I need to make this smaller. Okay. So that was step 3. Step 4 is going to allow me to find the other quantity that I haven't found yet, the child tickets. What did it say to do on step 4? Put it back in. So put it back in to what? Yeah, we could either, there's actually 3 locations where we could use. They're all going to be finding the same answer. I could put it in here, I can put it in here, or I could even put it in here. Which one's the nicest to put it into? The third one I did, right, where it says x equals, because it's already solved for x, don't you agree? So if I put it into this one, x would equal 562 minus 325. What would x be? 237. Okay, so now we're going to check it. I'm going to have you check it with your calculators because these are a little bit larger numbers. We're going to make sure that it actually works in the original first equations over here, okay? So if I take 325 and I add 237, do I get 562? Okay, so it works in the first one. Now you're going to have to do the calculation with the multiplication. So you take 5 times 237. I'll write this one down. I'm putting it into 5x plus 8y equals 3785. So we're going to take the 5 and we're going to put in the 237. We're going to take the 8 and we're going to put in the 325. Did it work? Yes? Excellent. So we have the right solution. And then step 6, so this is step 5. Step 6 is to write our solution either as an ordered pair or as values with units. Which one is appropriate for this problem? The units one. So x was 237. And 237 was what? There are 237 child tickets sold. And then there are 325 adult tickets sold. Okay, any question on that one? Okay, so not every problem is going to start out with context, and not every problem is going to be in a location where you actually have to solve the first equation. Sometimes they actually start with something where it's already solved for a variable. So you kind of get a bypass step 1. That happens sometimes as well. And it doesn't always have context, which means sometimes your answer at the end will be an ordered pair. It just depends on the problems. All right, the other way that we can solve this, well, this is the third way because I've already mentioned graphing, is called the elimination method. And I want to add in here that it's also sometimes called the addition method. Different textbooks use different phrases. Yours uses elimination. All right, so step 1, if necessary. This, again, is not always necessary. Multiply both sides of one or both equations by a suitable number so that one of the variables will be eliminated when you add the equations together. So in other words, like x, you want them to both have the number 5, one of them to be positive, one of them to be negative. Or maybe it's y, and you want them to both have the number -2, or both have the number 2, so one of them is +2, one of them is -2. You want the numbers to match, but the signs to be opposite. The reason you want to do that is because when you add 2 and -2 together, you get 0, and something then becomes, nothing. It cancels out. The second step is to, in fact, add the equations together so it eliminates one of those variables. Solve the remaining equation. And then steps 3, 4, 5 are exactly like the steps 4, 5, 6 were on the other one. You back substitute your answer into either of the equations to solve for the other variable. You check your solution at least mentally by making sure that it works. And then you write the solution as either an ordered pair or quantity with units. And I chose examples here where we had to create them from scratch because this is as complicated as it gets, okay? So everything that you see in your homework should be like this or easier. I chose the most complicated ones on this section. At a bake sale, Cassandra sells 4 muffins and 6 cookies for a total of $18. Michelle sells 3 muffins and 11 cookies for a total of $20. How much does a muffin cost? How much does a cookie cost? Okay, so what are my unknowns that I have to identify first? Okay, say that again really loud, Leah.
How much a muffin costs?
Okay, so we need the cost. It's not just muffins, right? It's how much it's a muffins, let's do it this way, muffins cost.
Do you want us to use XY or can we just use M and C?
You can. Do you want to use M and C this one? Sure, we'll do it.
That way I don't.
M for muffin. I really need to stop using examples with food in them. And then we've got C for cookie, right? The cookies cost. Or if you wanted to write cost of a muffin and cost of a cookie, that would be even maybe a little bit clearer. Okay, so these are the things we don't know. Now, we know how many of everything. That part we know on this problem, right? We know the how many. Well, last problem we didn't know the how many of each thing, but we knew the price. Here we know the how many of each item, but we don't know their price. Slightly different. Okay, so the first statement actually says that Cassandra sells 4 muffins, 6 cookies for a total of $18. So she sells 4 muffins and a muffin cost M. So how much money does she make for selling muffins? 4M. This is like our ticket sales part where we were looking at the price. 4M. And she sells 6 cookies. So how much does she make from selling cookies? 6C, and she makes a total of $18. So this is equal to 18. On the second one, Michelle sells 3 muffins. So how much money does she make from her muffins? 3M. And she sells 11 cookies, so she makes a 11C profit on those. And it equals 20. Right. Okay, very good. Now, the thing is on this one that none of those numbers match, right? 4, 6, 3, 11. Now, sometimes they match. If they already matched, that would be amazing. We might have to multiply something through by a negative, then we'd be good to go. But again, I chose something that was basically the hardest you could see, so you can see what you do when they really don't match at all. All right, they don't. We need either the M's to match or we need the C's to match. If we get the M's to match, what would the number be for them to match? What's the smallest one that they would use? 12. And what you're looking for is what we call the least common multiple. So if you've taken number theory, we've done that before. If you want the C's to match, what's the smallest place where the C coefficients will match? 66, which is bigger than the 12, right? So I tend to think let's do smaller numbers instead of the bigger. But if you did the bigger, would it be okay? Yes, it would. So if I want the M's to match, they would both be 12. What would I need to multiply the first equation by to make that happen? 3. And what would I need to multiply the second equation by to make that happen? Okay, 4. And then you bring up a good point, Amy. One of them has to be negative because the whole goal is for the numbers to be the same but opposite signs. And I heard Amy say -4 on this one, so I'm going to go with the negative on the 4. Okay? So we're going to multiply through all of these now and see what matches. So I've got the 12m, and it has to be multiplied through everything. So it's not just the 3 times 4, it's 3 times everything. So I have 3 times 6c for an 18c. And then I have 3 times 18. What's 3 times 18? 54. Awesome. On the second row, I have -4 times 3, so that's my -12m. Those are going to match but be opposite signs. I have -4 times 11c, so that's -44c. And then -4 times 20 gives me -80. Okay, so the step 1 was right here. Step 2, if you take a look over here, step 2 is to add the equations together. So adding the equations together and solving the remaining equations. So that's the step we're on. So this is step 2 in process anyway. M's cancel. How many C's are left? What's going on there? -26c. And then what's on the other side, the right-hand side of the equation? -26. Wow, well, that was very friendly, wasn't it? Ooh. Okay, so what's my last step? Divide by 26, and for the sake of more space, I'm going to make this just a little smaller for us. Okay, so divide by -26, and I would get that C is equal to 1. Yay! That's the end of step 2. What did step 3 Sam supposed to do? Plug it back in. Where? Yeah, anywhere is actually very accurate. Usually we use one of the first 2 equations because this one doesn't actually have anything solved for anything to make it easier. So I'll just use the first equation. 4m plus 6c equals 18. And we found out that c is 1. So this is 4m plus 6 times 1 equals 18. 4m plus 6 equals 18. And then what? Minus the 6. 4m equals what? 12. And then, yeah, we divide by 4, and m will equal 3. Step 4 is our check step. So we want to check both equations. So the first equation should be working because we used it to find m. 4 times m was 3, plus 6 times 1 is 12, plus 6, and that's 18, right? So we're good to go on that one. And then we're going to do the same thing with the second equation. It was 3 times m, which is 3, plus 11 times 1. So that's 9 plus 11, and that equals 20. Also good. If you don't show me the check step, that's okay. You don't have to. You're welcome to grab your calculator, plug it in, but I strongly encourage you to check it. Because I don't know about you, but most of you, I mean, I don't know about you specifically, but most of you look and check the back of the book when there's back of the book possibilities, right? So why wouldn't you check it if you can? I mean, you can, so you might as well. Step 5 is to write the solution with the context, that's units, or in an ordered pair. Which one would we do for this problem? Units, context, because there's context to the problem. Okay, so what did we find when we found m equal 3 and c equal 1? What is that? The cost. So muffins cost how much? The muffins cost $3, and the cookies cost $1. All right, any questions on that? Okay, the last thing we're going to do today is we're going to take a look at how many solutions show up in different types of problems. So there are 3 possibilities for how many solutions 2 linear equations in a system can have. One possibility is that they could have 1 solution. That's what we found in the last 2 problems. Visually or graphically, that means they cross in 1 location. So your picture is that it looks like this. There is 1 location for an intersection spot. Okay, that's one of our options here. The second option is a system could have no solution, and no solution looks like the empty set notation from number theory. It's a 0 with the line through it. So if you want the number 0, don't put a line through it. It means no solution, okay? Graphically, there's no intersection. So how is it that we could have two lines and they have no intersection? Parallel. So these are parallel lines, okay? And of course, visually, that looks something like this.
Sorry, I'm confused on the very first one.
Okay.
So okay, so you're just circling the point of intersection.
Yes, just the location for it. And there is no location on the second one because they never cross. And then the third one says a system could have infinitely many solutions, and graphically it means it's the same line. So we'll see an example of what that looks like because that's one I actually put onto here. No, it's not. I'll tell you what that would look like in a minute. But it usually, well, I can do it here. It usually looks like two equations that when you try and solve them, eventually at the end you get to something that looks like, so you've got equation here and equation here, and you're working to solve these and so forth. I didn't mean there. In here, and you've added them together, say, and then like we just did in the last one, and you end up with something like 0 equals 0 at the bottom, or 5 equals 5, or 8 equals 8. It's a true statement, but you don't have any more variables left in it. They're just gone. And so what ended up happening is they gave you two equations like x plus y equals 3 and negative 2x minus 2y equals negative 6, where one equation is just a multiple of the other one. They're really the same equation. If you simplified both of them, they would become the same thing, okay? That's what happens here, and it's just two ways of writing the same equation. That's what happens when there's infinitely many solutions. Okay, so I have two examples for you for finding all of the solutions, if there are any, in the following systems. And it doesn't tell you how you have to solve them, so you can use substitution or elimination for these. And we're just going to decide together which one we want to use. So looking at this equation, these equations, which would you like to do, substitution or elimination? Elimination. Okay, so this one's awfully friendly because the y's exactly match. They're both negative, which is not what we want, but they have the same coefficient, which is what we do want. So how do we change something so that we could get them to have a different coefficient or different sign? Switch one of them. So how about we just switch the second one? Is that okay? So we'll multiply the second equation by negative 1. The first equation will stay the same. So x minus y equals 1. And the second equation will switch signs. So negative 2x plus y equals negative 5.
Do we not have to add 2 on the top, like the first one?
No, the first equation stayed the same. The only thing, so like this equation went here, identical.
Okay, so we're only solving for y.
Yep, and the second equation, yes, we can only do one or the other, Hannah, and we have to pick. So we could have picked x, but we picked y. Yeah. All right, so what happens when I add these two equations together? What happens in the x column? Negative x. What happens in the y column? Yeah, they add to 0. And then what happens on the constant column? Negative 4. How then do I solve for x? Divide by negative 1, and I get that x is equal to 4. How then do I find y? Plug it in. Where is the nicest place to plug it in? The first one. It's x plus y equals 1, and we have x is 4, so 4, thank you. X minus y equals 1, so 4 minus y equals 1, and then what? Y equals 3. And you probably can just look at that and not actually move the 4 and divide by a negative 1. You probably look at that and say, I know the answer. What do I have to subtract from 4 to get 1? And it's 3, of course. Okay, so there are a couple questions here. It says find all solutions. So what is my solution then? An ordered pair. 4, 3. And if I were asked on this one how many solutions I have, the answer would be 1. 1 solution. Okay, I showed you what had happened on the previous slide over here of what it ends up sort of looking like at the end when you have infinitely many. I did an example now of what it looks like when you have one solution. The last example here is what's going to show up when we have no solutions. Okay, these lines are actually parallel. We can do this for, well, first, what should we recognize about this particular problem? Yeah, the orders don't match. So the first thing we need to do is we need to get the orders to match. So I will take the second equation because I kind of like alphabetical order and seeing x's before y's. I'm weird like that. So I'm going to leave the first equation as 2x minus y equals 1. And I'll switch the order on the second equation. So I'm going to move the negative 4x to the beginning, and then I'll have plus 2y equals 3. So that's not really a step. That's just restructuring to get the orders to line up. And I kind of like the idea of ordering them to line up here if you want to do elimination. If you didn't want to do elimination, you could just solve the first equation, for instance, by y, or for y, and that would be okay too. Okay? If you want to try to get elimination here, what would we multiply and which equation and by what number? First one by 2. Okay, so if I take the first equation and multiply by 2, see, here's just some arrows going on, Hannah. They're just for you. You like my arrows? You're welcome. And then I've got 4x minus 2y equals 2. And the second equation is negative 4x plus 2y equals 3. What happens to my x's? What happens to my y's? So I'm left with 0 on the left. What do I have on the right? I have 5. Does 0 equal 5? No. This tells you it's no solution. And the reason you got 0 equal 5 is because there were parallel lines. So when you eventually added the x's and y's together, they had this canceling out going on. So this has no solutions.